Hello, I'm Venkatarun. Today, I'll talk about how to formally verify the behavior of congestion control. This is joint work with Meena, Ahmed, Mohammed, and Hari. Over the last 30 to 40 years that we've been working on this problem, people have proposed literally hundreds of different algorithms. And the typical design process goes like this. First, we come up with a new idea. We try it in the network that we were thinking of, and it works. We try it in a different network, and it breaks. Then we sit down, think for a while, come up with a fix, try it in the network where it broke before, and it works. Try it in the original network and it breaks. And this cycle continues. I'm sure anybody who's worked on congestion control is painfully familiar with this process. So why is congestion control so hard? Well, there are many different types of network paths on the internet, and it is difficult for anybody to keep all of them in their head and ensure that their algorithm can handle all of them. Indeed, for every algorithm that we're aware of, there are network paths where it performs 10x away from optimum. And this is why any paper that proposes a new algorithm is able to find cases where every previous algorithm breaks. This was also the result of a recent empirical study. And this is also our experience when Hari and I were developing Copa a few years ago, and I spent sleepless nights thinking of various different ways in which Copa would fail. And this is called the congestion control anxiety, because we never really know whether an algorithm would break. And to fix this and to fix my sleep, we developed CCAC, which uses formal verification, and it systematically searches through an exponentially large set of network paths to either find a trace that breaks the given algorithm or prove that no such trace exists. And with this, CCAC introduces the notion of performance verification, where we use techniques developed for verifying the correctness of software to verify the performance of algorithms. And we believe that this is applicable beyond congestion control. And particularly good candidates are heuristics that have poor worst case behavior. We said that congestion control is hard because the internet can do a large set of things. What are some examples? First, this is the ideal view of the internet, where the sender and the receiver are connected by a single constant bitrate bottleneck link, and there's a fixed propagation delay. We can represent this graphically as shown here. The blue line is the arrival curve. This is the cumulative number of packets that have been sent. The slope of this curve is the rate at which packets are being sent. The red line is the service curve, and the gap between these two is the delay. And this is what most theoretical treatments of congestion control assume this internet looks like. However, the internet is more complicated than this. For instance, Wi-Fi routers create large bursts of acknowledgements because they don't send acknowledgements as and when they arrive. They wait for a large number of acknowledgements to arrive, and then they send them in a burst to improve wireless efficiency. But this can confuse congestion control because not all variations in delay and rate are due to congestion. We also have token bucket filters on the internet. So suppose there's an app that is idle for a while and then suddenly bursts packets. A token bucket filter will also burst a little bit before sending at a constant rate. And this is done to absorb small bursts and to improve application performance. But contrast this to what a constant bitrate link would have done. And congestion control algorithms can be confused into thinking that there's more bandwidth available than there really is. We can also just have regular errors, such as operating system scheduling errors, that make the service curve look a little bit jittery and random. These effects can combine too. We can have token bucket filters and OS scheduling errors. So on the left, we have the picture that shows what theoretical treatments assume the internet looks like. And on the right is what it can actually look like. And theoretical treatments also often ignore other complexities, such as packetization or the fact that losses are detected through duplicate acknowledgements and timeouts. CCAC is the first tool and method that can theoretically reason about phenomena that were previously accessible only through empirical methods. And crucially, it includes sub-RTT phenomena, which can often be the determining factor in a congestion control algorithm's performance. And therefore, theoretical analysis with CCAC is much more likely to correspond to reality. And an icing on the cake is that a lot of the proofs are automated, which has two benefits. First, of course, it removes the tedium from the human. And second, there are cases where computers are just better than humans. And we'll see two examples in this talk. We said that CCAC is a tool that searches through an exponentially large set of network behaviors. This set is specified by the network model. A network model essentially decides for each packet if and when it is going to be acknowledged. In our case, this is decided by an adversary. Now, this adversary requires two properties. First, It should be powerful enough that it can emulate all the network behaviors we discussed earlier and more. And this means that if an algorithm works in spite of this adversary, it's also going to work in any network that the adversary can emulate. And second, the adversary shouldn't be so powerful that it can emulate behaviors no algorithm can handle. And this is how roughly the model works. Consider the arrival curve as before. The service curve is what an ideal link rate would have done. In the model, we give the adversary some region where it can pick any service curve that it likes. The width of this region is the slack the adversary has to emulate different types of effects. There are also lots of other constraints. For instance, the service curve cannot be greater than the arrival curve. Therefore, the service curve has to be in this region. The other constraints ensure that the model has the two properties that we discussed earlier. Now, if the adversary wanted to emulate a token bucket filter plus some scalar noise, it would pick a curve that looks like this. It can also pick any other curve in this region. And critically, CCAC does not specify any probability distribution over these curves. Therefore, it is non-deterministic and not random. Now, we need to answer, is the adversary powerful enough? Well, yes, because we prove that it can emulate token bucket filters, ACK aggregation, delayed acknowledgements, random delays, scalar errors, etc. We also prove that if it can emulate A and B, then it can also emulate a composition of these two phenomena. Is it too powerful? That's the second condition we had. Well, it is not really possible to know this for sure, but we believe that we struck the right balance, because when we use CCAC to break algorithms, the traces it generates are all plausible in real networks, as in we can imagine network paths where this would happen. We also took care while designing the model to avoid the excessively adversarial cases. The paper elaborates on this a little bit more. Here's an overview of how CCAC works. Core to CCAC is an SMT solver. An SMT solver is like a SAT solver that takes a formula as input and tries to find an assignment to the variables of that formula that satisfy it. If no such assignment exists, it proves that this is the case. And in this formula, we encode our network model. And in doing so, we had to solve a few challenges that are detailed in the paper. And this forms the core of CCAC. To this, the user specifies formulas that describe the congestion control algorithm and their query. Their query encodes what sort of behavior they're looking for. For instance, they could be looking for cases of low utilization. And then CCAC outputs either an example of a trace that has the queried behavior, for instance, low utilization, or a proof that no such behavior exists. These proofs work over a finite amount of time and for fixed link rates. We can put a human in the loop to produce proofs that work over variable link rates and arbitrarily long time scales. In this case, CCAC does most of the proving and the user is only left to do the interesting bits. We demonstrate this workflow using three algorithms, AIMD, BBR, and Copa. AIMD, of course, is the most classical algorithm, and conventional wisdom says that if the buffer is greater than a BDP, that means we have 100% utilization. And this is the sawtooth graph we are used to seeing. So consider a case where the buffer size equals the BDP. Packets will get lost when the congestion window exceeds the buffer size plus the BDP. And when this happens, the congestion window is halved. And as long as it stays beyond a BDP, we get 100% utilization. Now, if we have premature loss, then the congestion window can fall below the BDP. And this causes underutilization. And loss can happen, for instance, if the buffer overflows. And this can happen if the sender sends a large burst of packets that overwhelms the buffer. To understand when this happens, we ask the following query to CCAC. We gave it an example of a buffer size and the slack the adversary has, and we gave it this formula. This formula says, does there exist a T such that loss happened and the congestion window is small? We also need to specify the congestion control algorithm. So we do that also using logical formulas. So this formula says that if loss is detected, then the congestion window at time T should be half of the previous congestion window. The Boolean variable can decrease ensures that we do not halve our congestion window twice in the same RTT. For the increase side, we have a similar formula. Before we discuss what CCAC found, here's a quick refresher. The sender maintains an estimate of the total number of bytes in flight, and this is equal to the total number of bytes sent minus the total number of bytes acknowledged minus the total number of bytes that the sender believes are lost. And the rule is, if the congestion window is greater than the in-flight, the sender sends packets. This means that it bursts packets if the in-flight suddenly drops below the congestion window. And this can happen if one of these two variables suddenly increases while the congestion window does not decrease. So let's look at ACK clocking. Now, the bytes ACK increases when ACKs arrive. And when ACKs arrive, packets are sent. So if the ACKs arrive smoothly, the packets are sent smoothly. If the ACKs arrive in a burst, packets are sent in a burst. And if this burst is large enough to overwhelm the buffer, we'll have premature loss and therefore underutilization. One might wonder that if the network has a buffer size of only 10 packets, how can it generate a burst of more than 10 acknowledgements? Well, maybe the burst is being generated by the Wi-Fi router on the reverse path. The fact that packet bursts can cause the sender to send a burst of packets is well understood. But what is much more surprising and CCAC uncovered is that if the sender detects a large number of losses, that can also cause it to burst. But this is surprising because the congestion window should also halve when this happens. But CCAC circumvents this mitigation. In the paper, we prove bounds on when this happens, and we'll discuss an example now. First, the adversary orchestrates a series of events that lead to this state. Here, the buffer size is twice the BDP. The congestion window is 4 times the BDP. In this animation, we denote 1 BDP using 8 packets. At this point, the buffer is about to overflow, so the next packet is dropped. We've highlighted the third packet in red because when this packet is detected, the sender would have gotten 3 duplicate acknowledgements, which would allow it to detect this loss. These next few packets arrive smoothly and go through the queue successfully until we get a burst of packets. Now, this burst was orchestrated by the adversary by sending a burst of acknowledgements 1 RTT ago. And since this burst arrives when the queue is full, they are all dropped. The entire 8 packets, which is 1 BDP, is dropped. Now the sender does not send anything for a while, and this red packet gets acknowledged. At this point, the congestion window is halved because the loss is detected. And since now the sender stops sending packets because the in-flight is lower than the congestion window, for every new packet that is acknowledged, the in-flight drops. Now, the adversary 1 RTT ago had orchestrated the burst that arrives right now. And the adversary also ensures that these acknowledgements are also sent in a burst. Note that this burst was sent before the congestion window was halved. And therefore, when this red packet is acknowledged, the congestion window is not halved again because AIMD does not reduce its congestion window twice for the same loss event. However, the in-flight packets will reduce by 8 because 8 losses have just now been detected. And since ACKs also arrive in a burst, for each ACK, in-flight drops by 1 packet more to reach 0. At this point, the number of bytes in-flight is 2 BDP lower than the current congestion window. This means the sender is going to send a burst of 16 packets or 2 BDP of packets. This will overwhelm the buffer and lead to underutilization. We also studied Copa, and we asked CCAC whether there are cases where it can get low utilization. And it answered yes, it can get arbitrarily low utilization. Then we asked CCAC, let's modify the model such that it can only emulate one jittery network elements, where previously the adversary could emulate multiple jittery network elements. And then we were able to prove using CCAC that Copa will always get greater than 50% utilization. So what happened? Well, Copa's key assumption is that if the sending rate is less than the link rate, then the queue will nearly empty at least once every RTT. But what CCAC told us, which we did not realize while we were designing Copa, is that even if this assumption holds for individual network components, it may not hold for a composition of these components. That is, while both of these components empty their queue, they may not empty it at the same time, leading to a persistent queue. This is how we represent that graphically. Suppose the arrival rate is much lower than the link rate. This is shown by the blue service line. And the service curve of the ideal constant bitrate link is shown by the red dotted line. Now the sender may be followed by a bursty components, which accumulates packets together and sends them in bursts. And after this, we have the constant bitrate bottleneck link. And then the service curve is going to look like this. Now you'll notice that there is persistent queuing between the ideal service curve and the service curve of the final bottleneck link. And this is in spite of the fact that each of these individual components periodically empty their queue. We asked the same question for BBR, and CCAC again found that BBR can get arbitrarily low utilization. And what CCAC found is that BBR periodically tries to probe for bandwidth by creating a transient queue. But the network can absorb this transient queue and prevent BBR from ever realizing that more bandwidth is available. And when we sat down and thought about the CCAC model, we found that there is a mitigation for this, which is to simply double BBR spacing rate. And we believe this is the reason BBR computes the maximum rate over the last 10 RTTs, because that allows it to overestimate the rate and therefore have the same dynamic that would be achieved by simply doubling the pacing rate. Facebook independently found and implemented this fix in their production version of BBR, presumably because it gave them performance improvements. We said earlier that we can put a human in the loop to produce proofs over variable link rates and arbitrarily long time scales, even though CCAC itself works only over finite time horizons for fixed link rates. And to do so, we use steady state analysis, where we try to prove that no matter what the initial state is, the algorithm and the network will eventually enter something we call a steady state. Once there, it will never leave. So consider a state space that looks like this. And the steady state here is some set of states. And the idea is to prove that if you're outside of this set, we will enter it. And if you're inside it, we will never leave it. And with this, we've been able to reason about the eventual behavior of an algorithm, even though CCAC's theorems themselves are only over finite timescales. Now, suppose the user guesses that the steady state looks like this over the variables, the congestion window and the queue length. And this is the user's primary job, guessing the steady state, for which they can take CCAC's help, because CCAC can tell them whether or not their guess is correct. Now they prove if the congestion window is smaller than what the steady state requires, then it will increase. And it will increase by the end of t RTTs. Here the user can pick a t that is the smallest value, such that the theorem is true. And therefore, t is really a function of the congestion control algorithm. The more robustly responsive it is, the smaller t will be. They also prove if the window is too large, it will shrink. And if the queue is too large, it will also shrink. Finally, they prove that if the algorithm is already in the steady state, it will remain there. And with this, they've also implicitly proven that as the link rate, propagation delay, and buffer size change, the congestion window and queue length will move towards the right value. And this happened because all of these theorems we have on the right quantify over the number of packets in flight, the internal congestion control variables, and so on. Therefore, no matter what state the network was in before, it will eventually move towards the right stage. And how quickly it moves is determined by the constants in these theorems, which of course depend on what the algorithm is doing. And then once we have the steady state, we can prove properties about things like utilization and delay, where we prove a theorem that says, suppose the network starts within the steady state, then what is the minimum possible utilization? This is how we proved earlier that Copa will get at least 50% utilization in a restricted network model. Now we talk about how we represent the network model in a manner that an SMT solver can reason about it efficiently. The first thing we do is we discretize time. So now the arrival curve and service curve are no longer curves, but they're a sequence of dots. Now notice that SMT solving in general is NP hard. So for efficiency, we keep the discretization to be pretty coarse. So we only have about 1 to 3 time steps per RTT. This is perfectly fine for congestion control because congestion control works only over RTT timescales, but it does confuse certain things like what is the delay? The delay is the gap between the arrival curve and the service curve. But it's not clear here which 2 points we should compare. And since the discretization is coarse, this can actually matter a lot. So what we do is first we notice that the arrival curve can be any of the following curves. In fact, it is any monotonic curve that lies within this square. And then we say that therefore, the delay at the red point can be anything within this range. So we allow Z3 to pick any delay that lies in this range. And the guiding principle behind this design choice is that we want that anything that is possible in the continuous model should also be possible in the discrete model. This has two consequences. First, any bounds proved in the discrete version are true in the continuous version as well. And second, there are things that are possible in the discrete version which are not possible in the continuous version. Therefore, these bounds may be looser than what is there in the continuous version. And we use this technique to further understand how premature loss can happen in AIMD. So in the constant bitrate model, loss can happen only if the congestion window is greater than the BDP plus the buffer size. However, we saw in the example that loss can happen prematurely under the CCAC model. So we prove in CCAC that suppose AIMD has entered the steady state. Then if the buffer size is greater than this threshold, then the same threshold as above holds, as in loss cannot happen if the congestion window is less than or equal to the BDP plus buffer size. And here the threshold BDP plus CD is intuitively the BDP plus C, which is the link rate, times D, which is the adversary slack. So CD is the adversary slack in bytes. And if the buffer size is smaller than this, then loss can happen only if the congestion window is greater than the buffer size. And this is much smaller than the regular bound, which is BDP plus the buffer size. In fact, this bound is tight because we just saw an example where loss can happen when the congestion window is 2 BDP and the buffer size was also 2 BDP. Our network model is similar to those developed in network calculus. The key difference is that our arrival curve depends on the service curve through the sender, which implements the congestion control algorithm. And this complicates the analysis because it closes the loop and we can no longer use the mathematical techniques developed in network calculus. Instead, we use an SMT solver, which in our case is Z3. And this allows us to apply network calculus to congestion control for the first time. There is obviously a very long line of analytical work to understand congestion control. And this is enabled to understand the equilibrium behavior and long-term convergence of congestion control algorithms extremely well. However, all of this analysis relies on link models that assume either it's a constant bitrate link or some simple stochastic process. There is also work on verifying the implementation of congestion control algorithms. And this is complementary to our work because our work can be used to come up with a good specification for an algorithm. And then this work can verify the implementation of that specification to verify, for instance, that the C code implements the algorithm correctly. In conclusion, we'd like to say three things. First, CCAC provides the first mechanism to theoretically reason about various non-idealities on internet. And this includes sub-RTT phenomena. And this could enable the design of robust congestion control algorithms. And finally, CCAC introduces this notion of performance verification, which we believe could have wider applicability. Thank you.